Hi, I am Sanjay Patel. Today we are going to discuss properties of gamma functions. Let us recall what is the definition of gamma function which we have understood in the last lecture. So for any positive real number n, we define the gamma function gamma of n is defined as integral 0 to plus infinity or simply 0 to infinity x raised to n minus 1 into e raised to minus x dx. So this is our main thing. Now let us start proving properties of gamma functions, which are actually some theorems. So I will be proving these different results which are useful in our understanding of gamma functions. So the first one, prove that, this is the most important one, prove that gamma n plus 1 is equal to n into gamma n. Remember, n is any positive real number. So let us prove this. Okay. By definition of gamma function, we can write the value of gamma n plus 1 as integral 0 to infinity. Just you have to put here n is equal to n plus 1. So this becomes x raised to n into e raised to minus x dx. Correct? This is just from definition, putting n equal to n plus 1. Now I want to find the value of this integral. So what I am going to do is I will use the integration by parts rule. So this is my u and this is my v, and we will be using this rule, integral u into v dx is equal to u into integral v dx minus integral of du by dx into integral v dx. So you know this thing, integration by parts formula. So this is equal to say first u as it is, x raised to n, and integral of e raised to minus x dx, that is e raised to minus x into minus 1. So I can write minus 1 here. Integration of e raised to minus x is e raised to minus x into minus 1. And then we put the limits of integration 0 and infinity. Minus, I can write say integral 0 to infinity, here du by dx, that is derivative of x raised to n, is n into x raised to n minus 1, and integral of e raised to minus x is minus e raised to minus x into dx. Okay, so this I am just keeping as it is because a separate explanation is required how to compute this value 0 to infinity, and this I want to write by simplifying. This minus 1 I am writing outside, so minus plus, and this n is a constant that I can put outside out of the integral sign. So 0 to infinity x raised to n minus 1 e raised to minus x dx. But what is this? This is nothing but gamma of n. This integral is actually gamma of n. You see the definition of gamma n. Gamma n is integral 0 to infinity x raised to n minus 1 e raised to minus x. So I can replace this integral by gamma n. So this is equal to minus x raised to n into e raised to minus x. Well, let me write this thing by putting the values. First we put upper limit of integration here, and that we cannot compute. So I am writing just x raised to n e raised to minus x. Okay, at x is equal to infinity, which we don't know, and minus, I can put x equal to 0. So this becomes 0. Okay. And plus this is n into gamma n. This second integral is n gamma n. So finally I get this result. So what I need to find is only the value of this x raised to n into e raised to minus x at x equal to infinity, where infinity is not a real number. Let me call this as result number 1. Now for that x raised to n into e raised to minus x at x is equal to infinity, we can calculate using the help of limit. This I can express as limit x tends to infinity, say x raised to n upon e raised to x. Okay, because e raised to minus x is 1 upon e raised to x. So this limit, which is an indeterminate form, because when you put x equal to infinity, so it is infinity upon infinity form. So this can be evaluated using the L'Hospital's rule, what you already learned from your previous courses. So this I'll be writing, you know what is the L'Hospital's rule. So let me find the derivative, limit x tends to infinity. Limit x tends to infinity n into x raised to n minus 1. L'Hospital rule says that if you have an indeterminate form, then find the derivative of numerator and denominator separately and again find the limit. So the derivative of the numerator is n into x raised to n minus 1. Derivative of the denominator is e raised to x. Okay. So by L'Hospital's rule. Okay. Again, still it is infinity upon infinity form if n is greater than 1. So I can further apply the L'Hospital's rule for this second indeterminate form, and it is indeterminate if n is, say, strictly greater than 1. So I can write this as n into n minus 1 into x raised to n minus 2. The derivative of x raised to n minus 1 is n minus 1 times x raised to n minus 1. Derivative of the denominator is e raised to x. Again, it is infinity upon infinity form if n is greater than 1. Okay. So again, I am applying the L'Hospital's rule. Let me write two things: if n is greater than 1 and L'Hospital's rule. So let me write simply L'Hospital's rule. Further, if you continue like this in the next step, which is again indeterminate form if n is greater than 2. So again differentiating numerator n into n minus 1 is as it is. Derivative of x raised to n minus 2 is n minus 2 times x raised to n minus 3 upon say e raised to x, provided n is greater than 2 and by the L'Hospital's rule. Okay. So if we continue like this, then after some stage, say kth stage, the power of this x raised to the power of x, that is x raised to n minus k. Let me write this way. After some stage, say kth stage, we get limit x tends to infinity n minus 1, n minus 2, and up to n minus say k, and say x raised to n minus k. Suppose we get this after k steps. Okay, and if in this case, if x is this n is less than k, if n is less than k, then this I can write as limit x tends to infinity n minus 1 up to n minus k, and then upon I can write x raised to k minus n into e raised to x. If, now this is something important, I'm explaining in a simple form. If this n is less than k, that is n minus k is negative, then I can shift that x raised to n minus k in the denominator. And now if you find the limit of this as x tends to infinity, this tends to 0. So this whole limit becomes 0, because as x tends to infinity, 1 upon x is to some positive power tends to 0, okay, where that is a known thing. So what is the conclusion here is we have proved that the value of this x raised to say n into e raised to minus x raised to n into e raised to minus x at x is equal to infinity, is 0. Okay, so we have proved that the value of this term in result number 1 is 0. So 0 minus 0 is 0. So what we are left with is n into gamma n. So we have proved that gamma n plus 1 is equal to n into gamma n. So let me write, just substituting this result, substitute this value in result 1, we get gamma of n plus 1 is equal to n into gamma n. So the result is proved. As a consequence of this result, we can derive another interesting and very useful property of gamma function. Say here in this case, n is any positive real number. Here n is any positive real number. But if n is a natural number in this result, what happens is something interesting. So let me write that as our second result. So prove that gamma n is equal to n minus 1 factorial if n belongs to capital N. Okay. So the proof is again very easy. It follows from the above result. We know that gamma n plus 1 is equal to n into gamma n. Okay. So therefore I can write gamma n is equal to n minus 1 times gamma n minus 1 by applying this result or this definition, this property. Again applying the same property star for gamma of n minus 1, this part I can write this as n minus 2 gamma n minus 2. Every time you have to keep on subtracting, and remember that in this case, in this particular result, we have taken n as a natural number. So n into n minus 2, then the next step would be n minus 3 gamma n minus 3. Gamma of n minus 2 is n minus 3 gamma n minus 3, again by result star. If you continue like this, after some stage, what you will get is n minus 1 into n minus 2, n minus 3, and so on. Finally, you will be left with 2 into 1 gamma 1. So last value means when we write n minus n minus 1, that will give you finally 1. So 1 gamma 1 is the last step. Okay. Now what remains, here n is a natural number, and the value of this product of the first n minus 1 natural numbers is n minus 1 factorial. So this is nothing but from this to this step I can write n minus 1 factorial into gamma 1. But what is gamma 1? Gamma 1 is nothing but simply 1. Just another important value you can remember, gamma 1 by definition integral say 0 to infinity x is to n minus 1. So x is to 1 minus 1 e raised to minus x dx, which is equal to integral 0 to infinity say e raised to minus x dx. And this integral is minus e raised to minus x and 0 to infinity. So we get this, and this is equal to, I can write minus e raised to minus x at x is equal to infinity, and minus e raised to 0. Okay, and e raised to 0 is 1, and the value of the first bracket is 0. So this is 0 and this is minus 1. And this can be proved very easily that as x tends to infinity, 1 upon e raised to x tends to 0 by your concept of limit of functions. So this is 1. Okay. So what I have proved is gamma 1 is equal to 1. This I would have proved separately first. So gamma of 1 is equal to 1. That value you must remember. And finally I can substitute this gamma 1 here. So I will get gamma n is equal to n minus 1 factorial. So thus, therefore, gamma of n is equal to n minus 1 into gamma 1, which is equal, n minus 1 factorial into gamma 1 is equal to n minus 1 factorial. So the result is proved. Let us prove the next property, which is very, very important. So the third property, prove that gamma n is equal to 2 times integral 0 to infinity x raised to 2n minus 1 into e raised to minus x square dx. Okay. So let us prove. All these proofs are very simple, based upon simple rules of integration. We start with this. We have gamma n is equal to integral 0 to infinity x raised to n minus 1 e raised to minus x dx. In this definite integral, I would like to take a substitution. Say, let us take a substitution x is equal to say t square, because I want here 2n. Okay, so if I put x equal to t square, I will get 2n minus 2, so that I can be adjusted later on. And whenever you take any substitution in this definite integral, you have to change the variables as well as the limits of integration also, and replace this differential dx by the new variable differential. So this implies dx is equal to 2t dt, and also I can say when say x is equal to 0, we have t equal to 0, and x is equal to say infinity, we have t is equal to infinity from this relation. Okay, so putting all this in our gamma function definition, what I will get here is, therefore, gamma n is equal to integral 0 to infinity. This x equal to 0 is replaced by t equal to 0, and x equal to infinity is replaced by t is equal to plus infinity. And x is replaced by t square raised to n minus 1 e raised to minus t square. And dx is replaced by 2t into dt. So you will get this thing. Simplifying, what you will get is this is equal to integral 0 to infinity t raised to 2n minus 2, that this 2 I can write here, into t into e raised to minus t square dt, which is nothing but 2 times integral 0 to infinity t raised to 2n minus 1 e raised to minus t square dt. And you know, in definite integral, the variable is not important. So I can replace this t by x. So we get integral 0 to infinity x raised to 2n minus 1 into e raised to minus x square dx. Just replacing t by x. Okay. So we get gamma n is equal to this very important integral 2 times integral 0 to infinity e 0 to infinity x raised to 2n minus 1 e raised to minus x square. Let us prove the next and the last property of this gamma function in this lecture. So result number 4. prove that, say, gamma n is equal to, say, a raised to n into integral 0 to 1 x raised to a minus 1 into log of 1 upon x whole raised to n minus 1 dx, where a is some constant. Let us prove. To prove this, I will start with the right hand side, as it is looks something complicated. So consider the RHS, that is a raised to n integral 0 to 1. Remember, here gamma is expressed in terms of this integral where limits are both real numbers. In the definition of gamma function, limits of integration are not reals. One limit is infinity. Okay, so I am taking a substitution in this. Let us take the log 1 upon x, because there is n minus 1 power. So if I take something, say t, I will get t raised to n minus 1, which is required in order to prove that this is equal to, say, gamma function. So that gives some idea, and I will take log of 1 upon x is equal to t. Okay, and that implies I will get, say, 1 upon x is equal to e raised to t, because here the base is always e, and that gives me x is equal to e raised to minus t. X is equal to e raised to minus t. And now finding derivative, to replace this dx, I can write dx is equal to minus e raised to minus t into dt. Okay, and also when x is equal to 0, if I put x equal to 0 here, then what is the value of t? You can put x equal to 0 here also. So t is equal to, say, infinity. And when x is equal to, say, 1, we have, when x is equal to 1, we have t is equal to, if we put x equal to 1 here, log 1 is 0, so t is equal to 0. Fine. So putting all these values in this right hand side integral, what I will get is that integral is equal to, therefore RHS becomes integral infinity to 0, and then a raised to n is already there. Let me write that if I forgot. Yes, it is a raised to n. And now I will put the value of x, which is e raised to minus t here. So e raised to minus t, a minus 1. Okay, and log 1 upon x we have taken as t here. So I can put directly and write t raised to n minus 1, and dx. The dx is replaced by minus e raised to minus t into dt. Okay, so we can simplify this further, and we can change the limits of integration, because integral a to b fx dx is same as minus integral b to a. So there is a minus sign here. If I will make it plus, I can rewrite this as integral 0 to plus infinity, then this is e raised to minus ta, okay, and minus plus t, okay, and into t raised to n minus 1 into e raised to minus t dt. Simplifying this further, a raised to n into integral 0 to infinity, if you add these two, what you will get is e raised to minus ta into t raised to n minus 1 into dt. And Now in this integral, I want to take another substitution. Let me take u is equal to t into a. I want to get rid of this a here. So this implies I will get du is equal to a times dt, and therefore dt is equal to 1 upon a into du. Also when we have t equal to 0, we have u is equal to 0, and when t is equal to infinity, we have u is equal to infinity, follows from this substitution. Putting all these values in this above step means here what I will get is this is equal to a raised to n integral 0 to infinity e raised to minus u, and what is t? T is, from this relation, t is equal to u upon a. So I am putting it here, u upon a raised to n minus 1 is there, t raised to n minus 1, and dt is 1 upon a into du. So simplifying, this is a raised to n minus 1 and this is a. So you will get a raised to n in the denominator, and that will be cancelled with this. So we will get simply integral 0 to infinity e raised to minus u into u raised to n minus 1 du. Remember this a and a raised to n all will be cancelled. This is a raised to n minus 1 into a in the denominator. That becomes a raised to n, that will be cancelled with this. And now if we replace the variable, dummy variable u by x, what I can write is 0 to infinity x raised to n minus 1 e raised to minus x dx. Just replace u by x. So it is nothing but gamma n. So I have proved that this is equal to RHS. Sorry, I have proved that this is equal to LHS. Okay, so the result is proved. What I have proved is gamma n is equal to this integral right hand side. Okay, so we have proved right hand side is equal to left hand side. Fine. Let me rewrite that result. So thus gamma n is equal to a raised to n integral 0 to 1 integral 0 to 1 x raised to a minus 1 into log of 1 upon x whole raised to n minus 1 into dx. Okay, so these are all of properties, some of the properties of gamma functions. In the next lecture we will see some properties of say beta functions, and then we'll establish relations between beta and gamma function also. So till then, goodbye and thank you so much.